Hello everyone, as you can see the title, How Can Innovative Materials Transform Global Environment? So we face global warming, natural resource depletion. This leads to pollution, wars, hunger. So we need to act now because we want to prevent irreversible damages. Now imagine you have a magical solar panel. It is efficient, it is stable, but the most important, it's multi-purpose. It can directly convert light into electricity and power the world. It can remove pollution from the air, and it can also split water, which we have plenty now from planet Earth, and produce clean green hydrogen. So my research group at the Hebrew University is dedicated to find such magical solar materials. We study their physical chemistry, their synthesis, structure, and properties, and we test them in devices for solar energy conversion. So to make it magical solar materials, we require a magical synergy of properties. So already today, they are very efficient solar panels, but they have only one function. They convert light into electricity. But we need something which will be multi-purpose and stable and efficient and low cost and non-toxic. So we need a magical combination of these properties. To do that, slight error here, but that's fine. We need to first invest in new synthesis of those new materials. Once we'll understand the synthesis, we can move further on to combinations of new elements. Then we can get and achieve our magical solar panel. So as you see here, there's still much unknown. New chemical combinations should contain innovative magical materials, but the number is almost infinity, 10 to the power 25. And you see here, as the number of the elements increases, you also increase the complexity. But the question is more always better. Perhaps different is just as good. So the typical process of finding any magical material is very slow. And I'm giving you the most prominent example, which is superconductors and their functionality. It took 100 years to search for the magical combination of a superconductor which contains 6 elements. And you see that the functionality increases with the number of elements using conventional reactions. And I'm using now quotation marks. Conventional reaction basically is mixing elements and heating them. It's like shake and bake. Other examples you can see here on the right. However, new synthesis can achieve better performance with few elements. This synthesis, which is not simple shake and bake, was identified 2 years ago. And you see only 2 elements were required to get a 2-fold increase in the property of superconductors. So there is still hope. Now, as I like to use food as a metaphor. And making materials is like cooking. It requires ingredients and heat. So I like omelets. I'm using omelets. Also I like cake, but let's stick with omelets. First, we need to invest finding new ways to make better omelets. Here you can see an omelet. We just need one bite to understand if it's a good omelet or a bad omelet. Here, this is an omelet that we made in the lab. It's an actual photo. This is a solar panel made in our group. But we just need to measure one small area of this solar panel to understand if it's good or bad. But to prepare and taste many omelets is very slow. So here you see 100 omelets that I made and then tasted all of them. It took me 3 months. So it takes a lot of time. So we need a different approach to finding magical omelets. We need to accelerate the search. And to do that, I'm using high-throughput cooking, which accelerates the discovery of magical omelets. I'm making many omelets at the same time, but I'm creating a gradient of some property. Could be temperature, could be thickness, and I'm just talking about the synthesis or the cooking. I'm not mixing too many ingredients altogether. So I do that with powerful lasers, which can form plasmas that condense on a frying pan. Basically, a plasma is a state of matter closely related to a gas, but the molecules are slightly charged. And you know this plasma ball that we used to have as a kid. Some adults also have this. Basically, inside there is a gas that when you touch it, you slightly ionize the gas, you see those sparks. So I'm using eggs as a material that I ablate. I shoot a pulse, very powerful laser, and I create a plasma. The plasma condenses on the frying pan, which is a substrate, and I'm making a film of omelets. I can make 1 omelet, I can make 100 omelets, I can also make 1,000 omelets if I'm just using rational design of the synthesis. And this system, this is an actual photo, is called pulsed laser deposition. So you have the laser pulse, which hits a target. You have the plasma, which condenses on a substrate. And here you have your omelet. So many omelets are measured using robots at fixed points. So here you have the small omelet, 1 omelet. Here you have 100 omelets. But how do I measure them? I'm using a scanning robot. So this robot actually comes and measures different points that I define in advance, and it tastes those points. So now I can get a map of flavors and understand which direction I need to go and how to plan my next experiment. So you can see the difference between using the old approach and the new approach. 3 months, same number of omelets, 1 week. Could be also faster. So now let's talk about magic. If you want to make magic, it is good to begin with things that we know, and we all know what rust is. It's an oxidized metal. We all know what rusty nails are. If you take the rust and you polish it off the nails, you can get a powder. If you purify the powder and you condense it, you get pure condensed rust. We take that rust, that target, we ablate it. So we have this plasma of rust. And we make an omelet made of rust. We have a rust panel. The problem is that the power is very low. We can actually make solar cells made of rust. But we use rust because it's a very good model material that you can study how other solar cells work. It's very stable because we know rust is a very stable material. But now, I'm telling you a little secret. We know that in the air we have 80% nitrogen. Nitrogen is not that reactive because we have rust. Rust is made of a metal which is oxidized. There's no nitrogen there. But if you can put the nitrogen, mix it together with the rust, it will be magical. Why? Because you have the oxygen and the nitrogen. They are slightly different properties. When you mix them together with a metal, you get something which is much more enhanced. And you can also tune the ratios between the oxygen and the nitrogen, and you can have a huge variety of properties. So what I'm doing in my group, I make plasma of nitrogen, and I react it with rust plasma. Basically, I'm making a magical rust panel. And it gives me higher power. So I'm using this magic to make magic solar panels. So to conclude my talk, we need to look over the horizon because magical materials would lead to global transformations. And thank you for listening, and I'm open to hear your questions.
Who's first? Okay. Please say your name.
Really interesting talk how the future of solar panels can look like. One question, how does your rust panel that you have right now in your lab compare to currently available solar panels? Are there advantages, disadvantages? What has to be done that you have a magical panel at the end?
Okay, so I will repeat your question. So we're asking how is a rust solar cell compares to a conventional solar cell that you see on the rooftops. So both of them have one function, which we don't want. We want a magical solar cell that will have different functions. That's one. The second thing is that rust, the problem with rust is although you can make a solar cell out of it, it has a very low conductivity. So you can create some charges, some electricity, but because the material is not that conductive, you are losing a lot of efficiency. So today, the solar cells that you see when you go to the Negev or on rooftops have almost the maximum efficiency that you can get out of these materials, and with rust, it's very low. But the reason we use rust as a material is because it's so stable. So we can use it as a model system to understand how broader system or more other materials can work. Did I answer your question?
Yes, thank you.
Thank you for a very interesting talk. Do you have any ideas how to add other properties to the Rust panel? This is the first question. And the second one, have you checked the long life of the Rust panel? Because you said that it's stable, but how the stability is connected to lifetime of this material?
Okay, so you asked two questions. I will repeat both of them. The first question that you asked, if I understand correctly, how can I tune properties of the material? So you need to picture that you have metal, but you could also have two types of metals. And you have oxygen and you have nitrogen. So at least you have three different elements. So if you play with the ratio of these elements and you maybe add another metal, so you already have 4 elements. And if you have a very high control of your synthesis, which in these systems you have, so you can tune the properties very much. That's one. The second question, you asked about the stability of rust panels. Rust is very stable. So you can put it on the roof and it can give you electricity for years and years to come. But because it's stable but inefficient, it wouldn't be a wise idea to put it on the rooftop. Are you asking about conventional devices, or we stopped here? Okay.
Also, if I can
Yeah.
ask one question more. Have you checked the oxidation state of the metal and how this influence the properties of your material?
So you're asking if I check the oxidation states of the metal. Well, it depends on the type of metal that you use, and also how many oxygen and nitrogen you have in the material. I mean, in one unit cell. So it has to be material specific to answer that question.
Okay, thank you.
Hi, thank you for the interesting talk. You might have explained this, so I apologize if I missed it, but you want your panel to have 3 properties: capture solar energy, capture carbon dioxide, and split water atoms?
Well, you asked if I want 3 properties.
Yeah, those are the 3. So I understand the first 2, but what would be the purpose of splitting water?
Well, water are made of hydrogen.
Okay.
And hydrogen, water is the only clean source of hydrogen that we have in the world. I mean, even today, hydrogen that you produce, the process is not that clean. And to use sun to split water in a clean way to produce hydrogen, you can't get more cleaner and greener than that.
So hydrogen would be captured and used for other purposes?
Well, hydrogen is a major component in our everyday life that we don't even fathom to understand. Clothes, food, manure for growing crops, chemical reactions. We need hydrogen in everything that we do, and I'm not even discussing transportation, any heat, commercial value.
Can I ask just one more?
Yeah, sure. I'm fine.
Of those 3 things, which do you think is the most challenging? The hydrogen, the carbon dioxide capture, or the solar energy?
So we already have enough solar cells that can do one function to convert light into electricity. The most challenging, I would say, although I'm coming from the field of splitting water, which is challenging by itself, the more challenging is capturing carbon dioxide from the air, because it's less than 1% and we need to concentrate it. So we cannot do that because we need to invest more efforts. So we need to have a very efficient system that will capture that carbon dioxide. So there is a lot of balance that you need to do. But to do the electrochemical or the photoelectrochemical reaction, that's the most challenging thing to do.
So, Ronen, thank you very much for this talk. I wanted to ask you, you said on the beginning that one of the most important things is the non-toxic nature of these panels. What about the toxicity of the Rust panels, and how are you going to assess the toxicity of the future magical panels that you're going to produce?
Rust, so basically you asked about toxicity. So how can I assess toxicity? Well, we already know what is toxic, what is not toxic. So Rust, so there is a general definition, a metal that is oxidized, but actually Rust is iron that was oxidized. It's iron oxide. Iron is, we have in our body, iron. It's not toxic. If you want to talk about specific materials, we need to gauge by the elements that we have in those materials. Tests that measure toxicity. So first you need to see what, you need to know, you know that because you do the cooking, so you know what material you put inside. But then you do stability measurements before you put that device out. Also in the lab, we do stability measurements in the lab. And there are some situations that the material decomposes, and then we see what is the outcome of this decomposition.
So thank you for the nice talk. You talked about superconductors. I'm not really a super expert, but usually superconductors work at very low temperature, if I'm correct. So is it a technical problem in your case when you do these studies, or simply you're used to that?
Okay, so you asked about superconductors, about the temperature and the functionality. I'm not an expert in superconductors. I gave you superconductors as a very prominent example of a material that took the entire 20th century to develop to reach to a certain point. The functionality that you saw, without getting into too many details, basically is the supercritical temperature. So we want superconductors to work at room temperature. We still don't have a superconducting material that works at room temperature. But what you saw on the y-axis was temperature. Now, each point on that plot also should have conductivity. But I'm not getting into that because you should assume that the conductivity is more or less the same, and what is more important is the temperature that you use that device, the material in a certain device.
Okay,
did I answer your question?
Thank you.
Thank you, Ronen.